Tableau 11, The Fabulous Limit Laws, Part 1, Chebyshev's Enduring Inequality and the Magisterial Law of Large Numbers. In Tableau 10, we had seen how, by consideration of polling systems, we found the binomial distribution emerging coyly from the ruins. An analysis of the structure of the binomial distribution showed us that there were good reasons for optimism in the conduct of polls. But it left begging the question of how effective a poll really is. To come to a right understanding of that kind of issue will require a little more digging into the structure of these distributions, into the probabilistic foundations. But the rewards are going to be rich. We are not only going to be able to characterize the quality of polling mechanisms very precisely, but in the process we are going to be able to discover deep underlying principles which apply to the theory of chance as a whole. So this then is our next subject, the subject of the fabulous limit laws. Let us begin by revisiting polling mechanisms to set the stage. So the student will recall that we were dealing with, in abstract, a dichotomous population. For example, two political parties which dominate a particular landscape, two creatures fighting for supremacy in, let's say, a certain part of the world. In a production process, the distribution of defective and non-defective merchandise, widgets, and so on. In the setting, one can imagine actually a physical population of two kinds of objects, say call them 1 and 0, defective and non-defective, for example. And they exist in a certain proportion. Let's say P is a fixed but unknown proportion of objects of type 1. And let's say Q, equal to 1 minus P, is the fixed but unknown proportion of objects of type 0. Our objective is to try to estimate P and Q. And the idea, of course, is by a random sampling methodology. If one selects randomly from the population as a whole, one gets members from 1 and 0, chance-driven. And of course, we realize that this is exactly what one gets when one tosses a coin. And so we are dealing with a setting where we have, as a sampling mechanism, a Bernoulli variable. So the basic idea here is we start with an underlying population. We generate a random sample by repeated independent trials. So here's a picture you've seen before, a table you've seen before, which shows you a sample of size 12, of which 3 of the 12 members were 1 and the remaining 9 were 0. Naturally enough, this is an abstraction of an underlying process. Right? And we quickly move on to a generic sample of size n, which corresponds to a repeated independent sampling, in other words, a sequence of coin tosses, with a coin of that fixed but unknown bias probability P. And now one obtains a random sample x1 through xn. We very quickly summarize the impact of the sample by forming an accumulated sum. So S sub n represents the sum of the x's, and of course this tells you how many 1s there were in the sample. And the moment we have this S sub n in hand, we now have a principle, a guiding strategy. We posit that the fraction of 1s in the sample, the relative frequency of successes in the sample, in other words, Sn divided by n, is a good surrogate for the fraction of 1s expected in the general population. In other words, we posit that Sn over n may be a good target estimate for that fixed but unknown P. This leads us into digging into the innards of the distribution of accumulated successes, and that led us to discover the binomial distribution. And the properties of the binomial distribution gave us several reasons for optimism for this procedure. The student will recall seeing a figure like this before, which shows you the mass function associated with the relative frequency of successes Sn over n, plotted for different values of n. To begin, the maximum likelihood principle articulated by R.A. Fisher gives us grounds for belief that Sn over n actually is the right choice as an estimate for p. The student will recall that the maximum likelihood principle in words says, what value of bias best explains the observed data, Sn? And an elementary calculation involving the binomial probabilities showed us that, in fact, the largest a posteriori probability of obtaining the observed number of successes Sn arises when we guess that the bias is exactly the relative frequency of successes in the sample, Sn over n. So, in other words, Sn over n is the maximum likelihood estimate of the bias p. A second reason for optimism arises from the form of the mass function. The mass function of Sn over n attains its maximum precisely in the immediate neighborhood of the value p. And so again, this gives us the largest probability, if you will, of getting that kind of value. Yet another reason for belief in the procedure arises from this idea of centrality captured by expectation, the probabilistic center of mass. The expected value of Sn over n is also exactly p. And finally, observing the nature of the graphs as n increased shows us that the binomial distribution gets increasingly concentrated around its center. We can put this in a more formal context by looking at the calculation of the variance or the expected squared deviation of Sn from its expected value. The variance of Sn increases linearly with n. It behaves like n times p times q. Or, since the variance captures the expected squared deviation from the center, if we look at the square root of the variance, or the standard deviation, divided by n, that should give us then the per unit or per sample spread around the center. And that, by a simple calculation, now becomes the square root of pq divided by the square root of n. This tells us that the per unit spread around p decreases like 1 over the square root of n as the sample size n increases. In other words, we've got increasing concentration near p, and this gives us yet one more reason to believe that Sn over n is a good estimate of p. All of these give us good, solid, principled reasons for optimism in our suggested procedure. But they are still lacking. And where they lack is in giving us any quantitative guarantees. How good, really, is the approximation Sn over n to p? What kinds of errors are we likely to make? Or, a more concrete question, for a given size of n, for a given sample size, what is the likely error? Now, digging into these aspects opens up a very rich and fecund region for exploration. Okay. And so this is what is going to be on our target for this tableau. Before we dive into the analysis, it would be wise to step back and take a look at the assumptions of the model, come to a good understanding of what we are expecting and what the main features are. Let's turn to this first before we return to an analysis of this issue.